Thank you and welcome to the virtual Mark Twain Library. We are delighted to have you join us today for this special presentation brought to you in partnership with Highstead, a regional conservation nonprofit in Reading. Our speaker today is Ed Faison, senior ecologist at Highstead, where he's worked since 2006. Ed has advanced degrees in ecology and environmental conservation from the University of Vermont, Harvard University, and the University of Massachusetts. His work focuses on long-term forest change, deer-forest interactions, the effects of land protection on forests, and natural climate solutions. His work has been published in scientific and popular journals, including Ecology, Conservation Letters, Connecticut Woodlands, and Forest Ecology and Management. So before we begin, please know that we have saved time at the end for questions. So you may submit your questions at any time throughout the program in the Q&A function, which is at the bottom of your Zoom screen. And we also are recording today's program. So you are, if you don't catch everything and you want to watch it again, or you want to let your neighbors know about it, please do. It will be in about a week. It'll be on our YouTube channel, the library's YouTube channel. And it will just be the presentation portion, not the Q&A. So without further ado, I would like to turn the afternoon over to Ed. Ed, thank you so much for joining us.
Thank you, Elaine, and good afternoon to everyone on the call. Thanks for coming today. So this talk will be based on a paper that I published earlier this year about carbon storage in our own backyards and how this relates to the climate change problem that we find ourselves in today and the relatively simple steps that we can take on our own properties to help make a difference. And the talk is geared towards the individual small landowner, but can also apply to neighborhood parks as well as larger areas such as land trust properties and other conservation lands. And just a note on terminology, I'll be using the term carbon dioxide and its chemical formula CO2 interchangeably in this talk. So I think we're all becoming more familiar with these types of headlines, unfortunately, and the impacts of climate change are no longer a theoretical projection sometime in the future, but are very much here today. More extreme weather events, including flooding, as this summer made all too clear here in the Northeast, as well as droughts and wildfire in the West. And not only does this affect us, but it affects other creatures that we enjoy and depend on, such as monarch butterflies and pollinating bumblebees. Coral reefs are the most biodiverse ecosystems in the world, and rising ocean temperatures are causing significant damage to them. And what is driving this change in climate? Well, I think most, if not all of us, are familiar with the idea that concentrations of heat-trapping carbon dioxide and other gases like methane are rising in the atmosphere. But just how unusual is our CO2 situation today relative to levels in the past? And scientists, by analyzing the gases and air bubbles trapped in Greenland ice, have found that CO2 levels today are about 40 to 50% higher than they have ever been in at least the past 800,000 years, and probably quite a bit longer. And these levels, of course, are far higher than modern humans have ever experienced. And although direct temperature measurements only go back to the 1800s in most cases, it is long enough to see a strong relationship between CO2 and temperature. Temperature is shown here by the blue and red bars, with temperature values on the left axis, and CO2 concentrations represented by the gray line, with CO2 values on the right axis. And you can see that the rise in both temperature and CO2 happened most dramatically after about 1960. And this CO2 rise is about 100 times faster than natural increases in CO2 in the past. And what is the source of all of this additional carbon dioxide in the atmosphere? And the answer, of course, is that it is us. And this figure shows global annual carbon dioxide emissions represented by up-pointing arrows, and annual carbon dioxide uptake or sequestration by the Earth represented by down-pointing arrows. And you can see that by far the largest up arrow is from the burning of fossil fuels, the gas, oil, and coal reserves and represented by this dark gray arrow on the left, which represents about 85% of the total annual CO2 emissions from the Earth. And now turning to the down arrows in our graph, and you can see that land vegetation, the light green arrow, absorbs the largest amount of CO2, while the oceans, the blue-green arrow, also absorb a significant amount of CO2 each year. And of course, plants absorb carbon dioxide through their leaves during the process of photosynthesis in order to grow and function. And they store this carbon in tissues such as wood. And trees and forests absorb by far the most carbon dioxide among all land vegetation types. So in fact, 92% of the carbon in the world's land vegetation is found in forests. Thus, trees are the best carbon capturing tool we have to remove elevated CO2 levels. And the problem is that we're degrading the best carbon capturing technology we have by removing our forests through wasteful timber harvesting, conversion of forests to roads and buildings, and by converting forests to other less carbon-rich vegetation types such as turf grass. And these land use changes are represented by the orange up arrow in the figure and comprise the remaining 14% or so of annual CO2 emissions. So where does that leave us? Well, even though the oceans and forests are doing an incredible service to offset our emissions, they simply can't keep up with the amount of CO2 that we're pumping into the atmosphere each year, resulting in almost half of the CO2 emitted each year remaining in the atmosphere and causing CO2 levels to rise each year. But there is some good news, and that is that land vegetation has tremendous potential to sequester a lot more carbon if we stewarded the Earth's vegetation differently. So for instance, even if we did nothing to reduce fossil fuel CO2 emissions, and I'm not advocating that we do that for sure, but just by allowing areas that are currently unforested, and this excludes all agricultural fields that we use for food and prairies where trees don't naturally grow. But if we allowed these unforested areas to naturally regrow back into forests, land vegetation could absorb almost another 1/4 of the Earth's annual CO2 emissions every year, leaving a much smaller slice of CO2 remaining in the atmosphere than we have today. And natural reforestation is one of several so-called natural climate solutions that would enable the Earth's vegetation to take up and retain a greater amount of carbon dioxide. And I'll be talking more about natural climate solutions and how they apply to backyard properties shortly. But the reality is we simply aren't going to remove all of the excess carbon dioxide in the atmosphere with natural climate solutions alone. We need to simultaneously reduce carbon dioxide emissions from fossil fuel burning and increase the removal of CO2 from the atmosphere to prevent the worst effects of climate change. And the good news here in New England is that each state has a plan to reduce their current CO2 emissions by 75 to 80% by 2050, which would leave just 20 to 25% of emissions remaining for natural climate solutions to take care of. And that is an achievable goal if we change our natural stewardship practices. Okay, so let's turn now to our own backyards, our neighborhood parks, and can these small areas really make a difference? And how might we steward the vegetation differently if we wanted to help the climate problem? And there are 4 characteristics that make backyard properties have great potential to contribute to climate mitigation that I want to talk about. Of course, not every characteristic will apply to every property, but I'll go into a bit more detail on each one of these. So let's start with fast-growing trees, and existing trees will generally grow very quickly and therefore take up carbon at a fast rate in our backyards. And because home properties, by definition, have a lot of forest edge with our driveways, houses, and yards, and it is this forest edge that results in faster tree growth. So if you look at the graph on the right, it shows annual growth rates over time for the same trees. First, when they were growing in the deep forest from 1950 to 1988. And then after the forest was fragmented for housing in the late 1980s, and the same trees were suddenly growing near a forest edge. And the growth rates eventually doubled after 1990 because of the increase in available light and reduced competition from trees that used to grow on all sides of them. And just to be clear, this is not an argument to fragment more forests to increase tree growth. There are all sorts of reasons that would be a bad idea, but in areas where we have already fragmented the forest for the construction of our homes, we can take advantage of the fact that our trees are growing fast and sequestering carbon rapidly. The second thing I want to point out is directly related to the first point, and you may have noticed that trees along roadsides and in your yards are often quite impressive in size. And this isn't an illusion or coincidence. Trees in our developed edge environments are often larger than trees in the middle of a forest. And those of you from Reading on the call may recognize this giant red maple on the left growing on town property along Lone Town Road across from Highstead. And this larger size of trees in edge environments is related to the growth rate of the trees along edges that I just mentioned in the last slide. So as an example, on my 1.5 acre property on a small residential street in Connecticut, I have 9 large trees above 28 inches in diameter. My old property of similar size had 5 trees that size. And an average 1.5 acres of Connecticut forest has only 1 tree that size. So that gives you a sense of the potential for backyard properties to harbor large trees. And it turns out that large trees store a disproportionate amount of carbon in the forest. So for instance, the 9 large trees on my property account for 4% of the total number of trees, but account for a remarkable 1/3 of the total forest carbon. And this is not unique to my property, but true in forests around the globe, as large trees account for somewhere between 30 and 50% of all carbon in the vegetation in these forests. And large trees also take up a lot of carbon each year. So this 40-inch or 100 centimeters, as my tape measure shows, diameter red oak tree on my property has added about 0.2 of an inch of wood each year to its trunk diameter for the past 4 years, which doesn't sound like much and is certainly a change that I don't notice with my naked eye, but it's a layer of carbon equivalent to adding an entire 6-inch diameter tree to the oak tree each year. So these large trees can absorb an incredible amount of carbon each year. So let me just take a moment to clarify the difference between sequestration of carbon and storage of carbon, because I've used both of those terms. And sequestration is the amount of carbon taken up each year by photosynthesis. So think of it as the size of a paycheck being deposited periodically into a bank account. Storage is the total accumulated carbon from sequestration over time. So think of it as the total balance of a bank account. Okay, so now even though backyard properties can have fast growing and large trees that sequester and store a lot of carbon, they still have driveways and lawns and a house, and therefore would not be expected to store as much carbon as 100% forest of the same area. But it turns out that my property stores almost 50% more carbon in the trees than an average 1.5 acre forest in Connecticut. My property is very likely unusual in that respect, but I doubt that it is unique. And so I just want to emphasize that properties with some existing woods may have surprisingly high total carbon storage on account of the large trees. But of course, it is much more common for backyard properties to have already lost most of their tree cover and to look much more like this. And the carbon stored on these properties is way below that of an average forest. And ironically, it is this very great carbon debt from past tree removal that gives such properties tremendous potential to sequester additional carbon if trees are allowed to grow again. And you can see just how much turf grass, which is comprised of lawn, golf courses, highway strips, et cetera, we have here in Connecticut and southern New England. We're pretty much leading the nation in percentage of land area in this condition. Okay, so let's turn now to applying natural climate solutions to backyard properties. And I'm going to reference three types of natural climate solutions: avoided conversion of forest, reduced cutting of trees, and reforestation. And which of these solutions is appropriate for a particular property will depend, of course, on what sort of past management has occurred on it. So is it predominantly wooded? Is it mostly open like the property on the right, or somewhere in between? Okay, so if you have a property that has some woods, like my property pictured here, then avoided conversion of forest to lawn is going to be a great natural climate solution option. This will retain the carbon in the trees and prevent it from being released into the atmosphere as CO2, and enable the rapidly growing trees to continue to sequester carbon going forward. So for instance, on my property, I have about 76 tons of carbon stored in my trees. And if I converted my forest to lawn, it would be a 99% reduction of the stored carbon in the vegetation. So by not doing this, the retained carbon stored in my trees is roughly equal to avoiding the annual CO2 emissions of 61 cars. So it's not an insignificant number of avoided emissions for one small property. And to put forest conversion into perspective across the state of Connecticut over a 30-year period from 1985 to 2015, the state lost about 115,000 acres of forest during this time. About 50,000 acres of forest was converted into turf grass, such as lawns, and perhaps the remaining 65,000 turned into residential and industrial developed land. And this loss of 115,000 acres of forest over 30 years translates into about 600,000 tons of CO2 emitted per year, which is equivalent to the annual emissions of 130,000 cars. So this gives you a sense of the potential reductions in emissions if we slowed down or halted forest conversion across many, many properties. Okay, so a property with some woods or even a single tree is also conducive to the second natural climate solution, not reduced cutting of trees. And the cutting could be from various reasons that include power companies cutting roadside trees near wires, or the owner cutting down trees to provide more light for the lawn. The key point is that any removal of trees will reduce the carbon stored on the property. And in the case of this property with a single tree, it will remove almost all of the above ground carbon on the property, which is stored in that single tree. So a few things I want to mention in the context of cutting fewer or no trees on your property is that to some extent, this will transfer some cutting and carbon removal to another property. So for example, I have a fireplace and the wood that I burn is brought from another property on the mine rather than cut from my own trees. So much of it is dying ash trees at Highstead that are cut down because they pose a hazard to cars along the driveway. And of course, there are carbon emissions from transporting the wood to my house by car and by burning the wood. And in fact, the CO2 emissions from burning wood are even higher per unit of heat in most cases than burning natural gas and oil emissions from a furnace. The other thing I want to mention is that if trees are cut down on a property, the ultimate loss of carbon to the atmosphere will depend on how the logs are processed. So if they are chipped up and burned, then essentially all of the carbon in the wood will be rapidly converted to CO2. If the trees are shipped to a sawmill, about 1/3 of the carbon stored in the trees may remain in the resulting boards as wood products, and this carbon will slowly decay and be reduced each year via decomposition. If the logs are simply left where they were cut in the woods, most of the stored carbon remains on the ground initially, but it loses carbon storage to decomposition over time as well. And how has past management and land use affected Connecticut's forest carbon storage? Connecticut's forests store on average about 35 tons of carbon per acre in live and dead trees today. But Connecticut's oak maple forests have the potential to store about twice that amount by the age of 150 years. So that is a lot of additional potential carbon that could be stored in the vegetation rather than in the atmosphere over the next several decades if we allowed more of our forests to grow older in areas that are protected from cutting. Okay, so returning to our third natural climate solution, reforestation, and here's the property in which almost all of the trees and stored carbon have been previously removed. And as I said before, the properties that have undergone the greatest loss in carbon are the properties that have the greatest potential to sequester additional carbon through natural reforestation. And natural reforestation means leaving the lawnmower in the shed and allowing nature to self-organize, which here in the Northeast means an open field will quickly start to grow back into forest without any help. So let's say the owner of this property decided to reforest 1 acre of this 5-acre field. And over the next 30 years, that 1 acre of regrowing forest could increase in carbon storage by 50-fold compared to keeping the acre as lawn. And that's not even counting the avoided emissions from a gas lawnmower during that 30-year period. So what is the additional carbon storage potential for reforestation across the state of Connecticut? Well, there are over 300,000 acres of grassy areas in Connecticut that are in lawns, golf courses, sports fields, highway strips, et cetera. And this does not include agricultural fields, by the way, which is a different category. And of course, many of these areas have limited reforestation potential because of their function, which requires them to remain open. But a substantial area of turf grass are lawns and fields that are kept open for aesthetic rather than functional reasons. So let's just say that the residents of Connecticut individually and collectively decided to reforest 1/4 of the current acreage of grass in the state and leave 3/4 of the acreage as is, simply by not mowing and letting nature self-organize. And over the next 30 years, this 78,000 acres could sequester an additional 10.5 million tons of CO2. And this would essentially offset the state's target reduced emissions of fossil fuel burning in 2050. So you can see the potential of reforestation to help the climate situation, even if we allowed just a fraction of the total open land to reforest. Okay, so let's turn now to the additional benefits beyond carbon storage and sequestration of stewarding a property for natural climate solutions. And I'll start with reforestation, since we just left off there in the last slide. And an area of lawn or field is in the process of naturally reforesting creates a very different and complex, AKA messier, habitat than the one that was growing there before. And almost immediately provides wildflowers like goldenrods for pollinating bees in the first few years. And in a few more years, if the reforested area is at least 1/2 to 3/4 of an acre, we can start to get species like blue-winged and chestnut-sided warbler, New England cottontail, and indigo bunting. And these are species that specialize in shrubby habitat and are uncommon in mature forests. So in other words, reforestation is a win-win for carbon and biodiversity in that it results in a steep carbon gain while also providing the uncommon habitat. Now, eventually, of course, these areas will grow to a stage of forest development where the habitat is less suitable for shrubland species, and a decision can be made whether to maintain them as young forests or let them continue to grow older. I'll talk next about reduced cutting on properties in a more urban setting, and large trees that are protected from cutting and retained on a property or in a small neighborhood park in urban areas function as biodiversity hotspots. And what I mean by biodiversity hotspots is exemplified in the study that showed that even 5 large trees greater than 40 inches or 100 centimeters in these small neighborhood parks can have 2.5 times the number of bird species than parks with the same number of trees, but smaller trees. And large trees have abundant flowers, pollen, nectar, seeds, and hanging bark, which all provide excellent food and habitat resources. And in a more wooded rural setting like my property that is connected to a larger forested area, retaining forest cover can provide habitat for species that use interior forests and some edge forests such as wood thrush, which use my property as part of their breeding territory. The wood thrush has suffered some of the steepest long-term declines among songbirds in eastern North America, as this graph from the Breeding Bird Survey shows. And in addition to habitat benefits, retaining tree cover and individual trees provides other key benefits, such as cleaner air by absorbing toxic chemicals like nitrogen and sulfur dioxide through their leaves and by filtering out particulate matter. And just like the biodiversity benefits of large trees also do a much better job of removing pollutants than do small trees. As a large tree, 30 inches or 76 centimeters removes about 60 to 70 times the quantity of pollutants as a tree that's 3 inches or 7.6 centimeters in diameter. And this is because bigger trees have more leaves and bigger canopies that can trap more particles than smaller trees. And it turns out that not all tree species are equivalent when it comes to removing air pollutants. Red oaks are better than red maples, and tulip trees are better than red oaks because filtering effectiveness depends on both leaf size and leaf structure. But even more striking is that the conifers, the hemlocks, pines, and spruces are generally better than deciduous species at removing pollutants because conifers often have these very dense canopies of needles, and they're also, perhaps even more importantly, they're evergreen species that retain their leaves as year-round filters. And you can see in the case of the non-native Norway spruce that it outperforms all the native trees in this graph in terms of pollution removal. So country of origin may not always be the best judge of a tree's benefits, depending on what benefit you happen to be measuring. So regardless of whether you have one tree between your house and a source of pollution or many trees, and this is my aesthetically challenged version of curbside appeal here on the right, it's going to make a difference, particularly if there are large trees with big leaves or are evergreen trees between your house and the road. Trees also have other climate-related benefits for a property, and those standing within about 60 feet of a house reduce home energy use and carbon emissions by cooling the house in summer and insulating it from cold winds in winter. And like the benefits of removing air pollution, large trees and evergreens provide the greatest energy-saving benefits. So for example, a 30-inch diameter red maple located on, say, the west side of a house would reduce carbon dioxide emissions by 6 to 7-fold compared to a 3-inch diameter red maple that is similarly placed. And one caveat is that trees, especially conifers located on the south side of a house, will increase winter fuel use slightly by blocking solar radiation. But unless you only have trees located on the south side of a house, the drawbacks will be more than offset by the substantial year-round benefits of trees located on the other 3 sides of the house. So the next benefit I want to talk about is aesthetics. One response to natural climate solution stewardship is, well, this is all well and good for storing more carbon, but who wants to live in a house that's closed in by trees and a dark and gloomy property without views? And that perspective is certainly understandable, as I think people generally do prefer a more open landscape with expansive views. But I like to think that my property, which is about as closed in with trees as it gets, and others like it, still offer much beauty and even expansive views at different times of the year. And I like this quote by Emerson because it speaks to the more subtle beauties that we sometimes don't appreciate as much. Okay, so the first and most important stewardship action one can take in regards to natural climate solutions is to sit back enjoy your trees and let them do their job. They're going to sequester more carbon and release less CO2 the less you get involved. And so it's really a triple win for your pocketbook, your trees, and the climate. And this is true not just for existing trees, but for reforesting treeless areas as well, as natural reforestation is generally going to be better for tree growth and biodiversity than planting a reforested area, and certainly much easier on your pocketbook. And planting individual trees is great for ornamental, shade, or screen trees, but it's going to be less good and far more costly for reforesting larger areas. And while you're enjoying your trees, if you're interested, you can use a forestry tape and measure the diameter of some of your trees, and then use the My Tree tool on the USDA Forest Service's iTree website, where you can enter the diameter of a tree and its location near your house, and it will provide estimates of carbon storage, sequestration, pollution removed, energy savings, and other benefits of your tree. And you can also use the US EPA's greenhouse gas equivalencies calculator website to plug in the amount of carbon calculated from the iTree site. And it will tell you what sort of CO2 savings in terms of, say, the number of cars driven per year you can expect from not cutting your trees. And even as you sit back and enjoy your trees, some routine tending will be helpful. Retaining trees, particularly the more beneficial large ones near your house, does have some hazards, as I experienced firsthand in August of 2020 when Tropical Storm Isaias rolled through, and this large branch broke off this red maple tree near my house and hit my roof. And so in the absence of my doing some trimming of branches, nature did the trimming for me, which was not exactly ideal. I have kept the tree itself standing, which continues to be healthy and provides a lot of benefits today. And rather than chipping up the wood after we cut the branch off the house, I deposited the branches into a brush pile or scattered them into the woods on my property. And now brush piles are definitely not going to help my property win any home landscaping awards. I know that, but they do serve as excellent habitat for a variety of small animal species at different times of the year. So the beauty is not in the brush pile, but in the biodiversity that the brush pile attracts to your property. Now, just as trees grow well in edge environments, so do vines. And Asiatic bittersweet in particular thrives in the edge environments characteristic of residential properties. And I probably don't need to tell most of you that. Bittersweet, as many of you know, will reduce the growth and carbon uptake and eventually kill trees by intercepting sunlight in the canopy and by strangling the trunk. So they are best cut and removed when they're growing up trees and over shrubs. And when I moved into my house 4 years ago, this bittersweet vine that I cut on the left was very large and all over this cottonwood tree. Now, grape and poison ivy are native vines and are generally more benign than bittersweet, but they do function similarly in edge habitats. I don't worry too much about these species, but when they are small, but when they get big and are in the canopy of trees, I do cut the vines at the base to give the trees every advantage of growth. No need to pull the vines out of the trees, particularly poison ivy. Cutting them at the base will kill them and they will fall down eventually, and you'll also avoid getting poison ivy. Over time, trees on a property will die from insects, disease, and other causes. And of course, they can pose a hazard if houses, cars, or recreational spaces are within the fall zone. So these trees may need to be cut down. But if dead trees are not a hazard, they provide considerable benefits if left standing, and are not an indication that the forest is unhealthy and in need of being fixed. Though no longer sequestering additional carbon, the standing dead trees continue to store existing carbon, often for decades, as they slowly decompose. Dead trees also provide nesting sites and food source for animals like woodpeckers and flying squirrels. And on my property, a standing dead elm tree was used for several years as a nest tree by yellow-bellied sapsuckers before it fell down. And like brush piles, dead trees per se won't win any aesthetic awards, but the animals that they attract, like this flicker, certainly could. And perhaps the best example of the habitat value of retaining dead trees is Eastern North America's greatest woodpecker species, the ivory-billed, which likely went extinct in the early 20th century because of a loss of large, dead standing trees in old forests that were logged. Now, over time, these dead trees will fall in the woods, or live trees will drop a large branch in a storm, as they did on my house, or perhaps fall down entirely in a big storm. And the temptation for many is to clean up these downed trees in the woods because they look messy. But large downed limbs and trees provide habitat for a host of animals, and they replenish nutrients and carbon to the soil and act as germination sites for new tree seedlings. You see this little guy coming out of this log. And they provide an increasingly important reservoir of stored carbon as a forest ages. So to sum things up, notice how the major natural climate solution actions that I've talked about today are subtractive in nature, meaning that they involve eliminating actions like mowing and cutting rather than adding actions to solve a problem. And sometimes the best solution to a problem is subtractive rather than additive, even though we tend to look for an additive solution. And that is certainly true if we wish to sequester more carbon and release less CO2 on our properties. So thank you very much.
Thank you, Ed. I greatly appreciate you spending the time with us tonight to talk about this and to give us a little motivation to see what we can do in our own backyards.